for the opportunity. Okay, so thank you for the opportunity to present here. So indeed, I'm going to present some stuff I did during my postdoc fellowship. So not everything I did, but part of it, at least. So the postdoc was in between the Memorial University in Newfoundland and Centre de Recherche Pétrographique and Géochimique, that is in eastern part of France, in Nancy. And so I worked with Aphrodite in Darès at Memorial, and Étienne Deloul in France, and Geoffrey Verwoerd in the US. And that was funded by the Marie Curie Fellowship. So today we're going to talk about high pressure metamorphism, but not only about high pressure metamorphism, also about timing of high pressure metamorphism. And timing is quite important, especially because you guys in Canada changed time last weekend and we didn't. So I was almost 1 hour late to my talk today. And good thing that I care about timing, in fact. So I cannot change. Okay, here, stood, click. Okay, so first comes first. Why high pressure? Because high pressure rocks are of kind of paramount importance when we're looking at collisional settings, because they record everything, at least most of what's happening at depth, and it can give us very good insight about the ways orogens are built. And especially if we put timing plus pressure and temperature, and especially pressure-temperature path. And that's quite important because if we look at rocks that are something like 30 kilobar, and then they're exhumed in something like 5 million years, we're not going to call for the same geodynamic scenarios than if we look at rocks that are something like 14 kilobar and exhumed in, let's say, 60 million years. So we need to find a way to accurately, let's say, date metamorphism, and not only metamorphism, but timing of metamorphism, rates of metamorphism, and timescales of metamorphism. And there's two ways, let's say two big end members to do that. First, we can go with looking at accessory phases. And the one that is the most studied is, of course, zircon, because zircon is theoretically quite easy to find. And we can date it with uranium lead, of course. We can also look at temperature with the titanium amount. We can look at fluids with oxygen, delta oxygen records. We can look at origins with hafnium records also. And if we look at the trace element record, we can also try to link it to specific PT stages. And that goes with the fact that when you've got no garnet that fractionates heavy rare earth element, then heavy rare earth element can go into zircons. And when you have plagioclase present, then you're going to fractionate europium, and then zircon's going to inherit kind of europium anomaly. And if you have no plagioclase and garnet, then you're going to get a specific, very specific spectrum with flat heavy rare earth and no europium anomalies. And then you can try to link that to specific PT stages in here. But the issue is going to be that zircon's not always recrystallizing properly and not always also recording what it should record properly, meaning that it's an accessory phase, so it's not going to decide what's going to happen with the trace elements, especially if you get something that's metastable in there. So sometimes zircon can lead you to improper geodynamic scenarios. And if we look at some zircon examples in here, they're pretty complex. This one especially is very, very complicated and convoluted. And of course, when you see those zircons, you cannot completely expect them to behave the way you want them to behave and to record what you want them to record. So then you can link dating accessory phases with dating major phases in metamorphism, and that would be garnet. And garnet, it's quite fantastic. Well, I think there's a lot of metamorphic crowd today. So I'm not sure you're going to be, I'm going to convince you on that because you're already convinced, I think. But you can date it with lutetium, hafnium, and samarium neodymium. So 2 chronometers. And that's quite useful because lutetium is going to be highly fractionated into garnet cores, while samarium's more going to enter garnet at the late stages of crystallization, meaning that when you date both of them, you can sometimes get the beginning, early crystallization, and then late crystallization. And then, of course, they also have different closure temperatures, so you can also have peak and cooling temperature. And your garnet strategy, your garnet dating strategy is going to be a bit different depending on your sample. And of course, you see here two complete end member with one big garnet and very tiny, tiny garnets in here that are not an outcrop. These are on my desk, in fact. So when you have huge garnets, you can go with sampling some specific zones. And especially in here, you can see some work done by Besim Dragovic et al. In 2012, where they micro-drilled part of the garnet and they got all these kind of rings in here. That was done in samarium using samarium neodymium. You can see also some cuttings done using a laser, and that's a work done by Laurent Tual et al. Well, 2 years ago. In fact, that's very, very recent. And last, you can also get some chunks in here, and that was done by Hao Chiang et al. In 2018, and they were looking at lutetium, hafnium, and samarium neodymium. And that works if you get sample garnets that are at least a centimeter. And of course, you want them to be very, very big. And of course, most of the garnets are not that big. And when they're not that big, you're gonna get bulk. So you crush your rock and then you pick out tiny, tiny crystals of garnet, fragments of garnets, and then you dissolve them. And that one is very time consuming, but that's the only one you can do when you have very small garnets or when you have garnets that are very, very low in lutetium and samarium. And then in whatever these 4 boxes, you dissolve them and then you do column chemistry and then you go to the mass spec. Very recent way to date garnet has been published by Simpson et al. And Tamblin et al. In 2022, 2021, which is lutetium hafnium in situ in garnets. But in that case, you need huge, huge concentration in lutetium, at least 10 ppm variation somewhere. And also huge garnet because the spots are something like 100 microns. So that's the way to date, basically, the 2 end members to date metamorphism. And we're going to look at that through the Grenville orogeny. So the Grenville orogeny in here is a 1 billion years old orogen. You can see there's many, many outcrops across the globe. And the Grenville province, sensu stricto, is here in the northern part of the American continent. And it results from the collision between Amazonia and Laurentia. And it's subdivided into two big end members belts. You've got the parooctonous belt and the alloctonous belt. The alloctonous belt is subdivided into the high pressure here in purple, the mid pressure belt here in purple again, and low pressure belt in a different way of purple. And then you've got the parooctonous belt with high pressure again and low and mid pressure belts. So these are mostly granulitic with the metamorphism, and it's also intruded by some anorthosites during the Grenvillian orogeny. Looking at it, in fact, you see that you have kind of different high pressure outcrops. In the south, you have in the western part, in fact, of the Grenville orogeny, you've got mostly mafic pods of eclogite that are retrogressed to granulate facies, and these are dispersed in orthognaces. In the central part of the Grenville, you've got a coherent lithotectonic package where you have something like 2,000 kilometers thick like stack of mafic granulate to eclogate facies rocks. And then in the parooctonous belt, in the Molson Lake terrain, you've got eclogitized metagabbros. So what we know about the Grenville orogeny, we have most of the first order stuff that were published in the 2000s and so by Jamieson and Rivers and so on. And if we look at very schematic sketch, first comes first is the early collision at 1090 to 1050. And during that stage, you build up a high plateau. And because of that, so you double the crust, and then at the base, you're going to develop high pressure granulate facies, high pressure metamorphism. And that is extruded laterally by channel flow in here at the front of the orogen. And that's your high pressure metamorphism. Then you've got gravitational collapse from 1050 to 1020, and then a tectonic hiatus just in between here from 1020 to 1 billion, where nothing is supposed to happen. And then you've got the the last phase, the Rigollet phase, at 1 billion to 980 million years. But we don't have that much data on the high pressure rocks. In fact, when we look at the literature, we have two published articles from Marshall and Kulshaw in 2014 on uranium, lead, on zircon and trace elements and so on. And Gaidiz et al. Just a few months ago published a lutetium hafnium, in situ lutetium hafnium in garnet study. But what we're looking at today is this zone where we have the most coherent lithotectonic package, the Manicouagan imbricate zone within the Central Grenville province. And if we look deeper, and so the Manicouagan imbricate zone in here is the amalgamation of two units. You've got the Chenukutish unit in here in dark purple, and in here the Lelucio terrain in, let's say, light dark pink. And these two are mostly anorthosite, mangérite, charnokite, granodiorite rocks at 1.6 billion years. And on the south part of the Manicouagan reservoir in here, you've got some meta-aluminous rocks that are mostly migmatites. And then just below, you've got the mid-pressure, just below, well, it's overlaying, because the mid-pressure belt and the Pauctonous belt in here in the north, just in between the Grenville front and the Lactonous boundary thrust. And if we look at the metamorphic ages in there, there's a lot of data that have been acquired by the Memorial University group mostly in the meta-aluminous rocks, and this is what you see in here in the Chenukutish terrain. And in the Lelucio terrain that represent most of the unit, and you can see just in here in the tiny sketch, it's most of the Manicouagan imbricate zone. There's not that many data, and in fact, there's a lot of uncertainties on the date, and there's also not very specific links to metamorphic stages. We've got few data which are upper or lower intercept zircon and so on the AMCGs, but nothing on the mafic, and the mafic are the ones that are going to record the best the early stages of metamorphism. So that was the idea, one of the ideas of my fellowship at Memorial, look a bit deeper into the record of the mafic rocks in the Manicouagan imbricate zone. So today I'm going to present two samples, one in the western part, that's going to be yellow stuff, and one in the eastern part that's going to be a bit greenish. If we look into that, they're quite nice, in fact. They're textbook high-pressure granulite. They're pervasively recrystallized, and you can see that on the SEM MLA maps here, which is a scan of the thin sections. And granoblastic texture, you can see it here on this nice picture. You can see nice big garnet that have not that much of inclusion, mostly kyanite inclusions. They're in complete equilibrium with the clinopyroxene that has a diopside composition. You've got plagioclase, pargasitic amphibole, and some scapolite also in here. And the sample is quite homogeneous when you look at it at the sample scale, but also when you look at it at the thin section scale. And you've got something like 30% of garnet, 30% of diopside, and about 20% of plagioclase in there. And amphibole is about 10%, so not that much, not that many hydrous phases. And you see these purpley things that was here. These are scapolites. When you look at garnet chemistry, you see that cores are a bit higher in calcium. This is a grossular profile through 3 grains, in fact, 1 big grains, and which are the amalgamation of 3 subgrains. And when you look at plagioclase and scapolite, just in here, okay. You can see that the scapolite have a in between sylvialitic and meionitic composition, so in between the SO4 and CO3 end members. And when you recalculate them to see if they fit the plagioclase composition, to see if there are a phase of just plagioclase alteration, they are different. Yeah, okay. They are a bit different. So you can see that you have a bit more albitic composition for plagioclase, and here in very light yellow, this is the recalculated scapolite. So scapolite appears to be at equilibrium, and there appear to not be a phase that is just retrogression of plagioclase or alteration of plagioclase. So, of course, the first thing is to try to find some PT on that. So I did some thermodynamic modeling using Teriac domino. The input for this rock was very specific because there was no manganese, no titanium, and no potassium in the whole rock, something like below 0.6 weight percent. And I also compared that to the local equilibrium at the scale of the thin section, which was basically exactly the same. For the input also, I used the exact proportion for water based on the amphibole proportion. And then there was some kind of reflection about the scapolite situation because we don't have any solid solution model that is appropriate for scapolite. So what do? Either we keep it and then we have an excess in aluminum and silica. So then we're going to overestimate some quartz and some kyanite and probably overestimate some garnets and plagioclase. Or we can try to remove it, but then we are impairing all the equilibrium and it's kind of an oversimplification. So in that case, we did both and we get the best fit, in fact, not removing scapolite, so keeping it and using it, and it's probably going as plagioclase. And what we see first is that, okay, the eclogat facies is limited in here by the plagioclase reaction line, and the temperature is limited here by the liquid, the melt reaction line, in fact. And our paragenesis, garnet, diopside, amphibole, plagioclase, and quartz, is basically stable in between 14 to 16 kilobar and something like a bit less than 800 up to 900 degrees. And it's confirmed by the mineral mode, so the proportion of garnet, of clinopyroxene, and of plagioclase that are a very good fit with what we see in our samples. But it's also validated by the garnet isoplates, so the grossular isoplates in here and the magnesium iron ratio in our garnets. So we have a good fit of our data with what we knew from the literature, which was something like 14 to 16, 17, and 800 to 900 degrees. And then, of course, the idea is to go for the timing. And first, we looked at the zircons. So zircons are quite complex. As you can see, you've got some very specific cathodoluminescence texture. So here you've got a very dark inner core, and you can see also some magmatic remnants in there. You can have, again, the same kind of core in there, and then sometimes multiple rims on top of it. So rims that can be 1.2, rims that can be around 1, and so on in here. And sometimes you can also get rims that can be 1.4. One systematic, though, is that cores in there are either 1.4 or 1.6. And if you plot them into a Concordia diagram, you can see that it's a bit of a kind of a mess, in fact. We have all the ones that are in the 7, so the lead 207, lead 206 ages that are something around 1.6, and they fit all on a discordia that is related to recent lead loss. And then you have some that are in between. You got the one at 1.4, you got the one at some rims that are 1.2 for the 207, 206. And then you've got very, very few that are around 1 billion year. So either there is a continuous lead loss or maybe multiple lead loss events. And if we look at the data a bit differently, we can just plot them in a density diagram. And you can see that we have something that can even look like sedimentary, in fact, detrital zircon stuff. And we have one peak in here at 1.4, a tiny peak at 1.2, and one peak at 1.6. And if we look into the chemistry of our zircons and the trace element record, we have absolutely no europium anomaly anywhere. And we have mostly heavy rare earth element enrichment. So no europium anomaly would go with no plagioclase. We cannot expect for these rocks to be to just be without plagioclase for that long, from 1.6 to 1 billion years. So there might be some other explanation, in fact, that could be that europium is not 2+ but 3+, and meaning that it can go easily into zircon, or maybe, and that would say that we have an oxidized, in fact, state in our sample, or maybe we have zircon that crystallized before plagioclase, but then we need kind of pocket effect if we are in a magmatic chamber to crystallize zircon. So there's different ways to interpret that, and also it could be kinetic disequilibrium. You see that you have three spots, in fact, 3 spots in the grain that are rims at a bit younger than 1.4 billion years. That's record flat everywhere of patterns, and they're not very specifically linked to any stage, in fact. So either we're going with there's a lot of disequilibrium in that sample, or we can go with these are coming from different sources, and this might be a metamorphosed mafic sediment. Of course, the good thing is that we went also with garnet dating. And if we look at garnet, so we separated, oh, I forgot, all of these data are obtained by SIMS. So this is not laser, this is SIMS. So this is a very tiny 10 micrometer spot that we did on all of them. So if we look at the garnet, we separated 6 fractions of garnet. So this is bulk, and from these fractions, so all of them, we subjected them to dissolution and to spiking in lutetium hafnium and samarium neodymium. So first, the lutetium hafnium data in here. So this tiny zone represents 2 points, let's say model age, with 1 whole rock and 1 garnet fraction, and it helps to see how much the data are coherent or scattered also in a different way than just looking at the isochrone. So these garnets were quite complicated because they were very, very low in lutetium and hafnium. So 0.6 ppm of lutetium on average in those grains, and 0.1 in hafnium. You can see also in here that you have quite a variation in between the whole rock bond that is dissolved under high pressure and the whole rock savilex, which is dissolved on the tabletop. So this highlights, in fact, the accessory refractory phases contribution, and they're quite well aligned. So that's kind of good because it shows that zircon at least didn't hamper all of this record. And then when we look at the trace element patterns, and this is trace element normalized to chondrite, and these are obtained through a grain. So this is sampled through a complete grain in situ with the laser. And when you look at it, you see that the edges in here are enriched in heavies, and the core and the mantle, in fact, are a bit depleted in the heavies, which is not what you expect in garnet. Most of the time you get high fractionation of lutetium in the core, and then you get low lutetium in the rims because of relay fractionation, meaning that, and suggesting also that it could be that some phases were keeping the lutetium away from garnet when garnet started to grow. Finally, the age. The age is about 1020 plus or minus 7 million years, which is quite young, if you remember what we said at the very beginning of the talk. And when we look at samarium neodymium, done on the same fractions, just 1 to 4 that time, because we stopped just at 4. And this is 1 billion years, plus or minus 13 million years. And both of them are quite, in fact, equivalent within the uncertainty. It's joined at something like 1010 or 1012. In these garnets, the fact that we have quite good crystallization, we keep also some part of the prograde with the calcium zoning, and the temperature we reach, something like 800 and so on, we can approximate peak high pressure peak granulate facies at something like 1020, which would be the lutetium hafnium age, and fast cooling at 1 billion years, just following that. So if we sum up, high pressure granite facies is about 14 to 16 kilobar in that zone, 800 to 900 degrees. Peak high pressure granite at 1020 million years. And then zircon, lack of successful crystallization, because as you remember, zircon were everything but 1 billion years old during high pressure, high temperature metamorphism. And that might probably be because of the dryness of our sample and the fact that we don't have any evidence of partial melting whatsoever, any evidence of retrogression whatsoever. And if we look at what's happening in here, in the eastern part of the Lelucco terrain, so sample KWs, we have very nice samples. In fact, that one was my favorite sample, but it was quite complicated, as you see. So you've got these nice garnet porphyroblasts, in the core of which you can see some tiny needles of kyanite, some tiny needles of quartz also, sometimes a bit of corundum. And this is exactly the kind of frozen Gaspio reaction between plagioclase that leads you to garnet kyanite quartz. And in this sample, you have some nice clinoparxine just in here. You've got edenitic amphibole, and you've got also plagioclase, of course, and scapolite. And if you look at plagioclase, you can see here on the SCM MLS, plagioclase is the gray zones. You see some kind of what would you would think it would be a foliation, but no, it's not. This is in fact some big plagioclase domains that are very locally pseudomorphed, in fact. So in these zones, you have the inner part of the domains that are more calcic and the outer part of the domain that are more sodic. And this is locally recrystallized big domains of plagioclase that are mimicking the magmatic texture. If we look at the trace, the major elements in garnet, again, you see that you have the core that are richer in grossular, and then the rims that are depleted in calcium. And this is what you see on this very nice map. So the warmer the color are, the most you get of calcium. And what you see on the very outer part of it here in blue is the outer rim that is completely different than the rest of the garnet. And this is also seen when you look at the trace elements in there. And in fact, you look at the rim in here, they are completely different compared to the inner core. And this is not an ongoing depletion. This is a very dramatic depletion in here. In between, there's a big jump. It's not continuous. So you've got the core and the mantle that are just classic trace element patterns in garnet, and then completely depleted without any continuation in between. And when you look at the lutetium hafnium ages, again, these obtained on 6 fractions. And this fraction was separated using the fronts, meaning that there's some fraction that are not coming from the same magnetic pool. And when you look at the residues, because as you see, there's some kind of scatter and some kind of dispersion in here. And when you look at the residues, in fact, you get kyanite in the fraction 5 and 6, meaning that kyanite is the needles you get in the inner part of the garnet. And that helps us to interpret these ages that are older, that like representing the very approximating, not represented, but approximating the garnet early growth at 10-30 million years, plus or minus 6. And garnet rim, let's say average of rim, is about 10-13 million years, plus or minus 6 million years. Again, very low lutetium and hafnium in these garnets, something about 0.2 ppm of lutetium and 0.08 ppm of hafnium. And as you can see with the trace element patterns, with the, you see here the calcium map and the ages, we probably have 2 garnet growth stages. And again, on these, we have also samarium neodymium that are in good agreement at 1 billion years, plus or minus 8. And this is also equivalent within uncertainty with the lutetium hafnium younger age. So this can approximate first garnet growth at 1030 and then second garnet growth at 1015. So if we sum up for the eastern Lelucco terrain in here, we've got the lutetium hafnium age at 1030, first garnet growth, then lutetium hafnium age at 1015, and samarium neodymium the same, second garnet growth. And this is also the time where you get peak high pressure metamorphism in the western part of the Lelucure terrain. So if we zoom out and look at everything, first, we can say that in the Manicouagan imbricate zone, we have high pressure granite facies that straddles the Otawan to Rigollet stages, meaning just in between the two massive orogenic phase. Remember, Otawan is 1090 to 1020 and to 1030, sorry. And then Rigollet is something like 1 billion to 980 million years. Second, we have localized crystal thickening at the margin during the propagation of the orogen towards the Grenville front. And this is shown a bit in this cartoon in here, where you get the high pressure zone, the Manicouagan imbricate zone in here, just in between the Petrochronological and the mid-pressure belt. And you've got edges that are younging towards the Allochthonous boundary thrust, meaning that you're propagating the thrusting. First, and quite important also, in the Central Grenville at least, the high pressure belt and the high pressure rocks are not early extruded from the lower crust during the early collisional stage at the early Otawan. So meaning that they're not the base of a high plateau. And is there even a high plateau to begin with? And finally for that part, there's no tectonic hiatus during the Otawan and Rigollet phase, at least in the central part of the Grenville orogeny. And what we see in here is a tectonic continuum. If we zoom out completely and we look at the stage of the whole province, we're looking basically at apples and oranges. In the western high pressure segments in here, you've got eclogite pods in orthognaces and metamorphic ages as something like 1080 to 1097, so obtained by Marsh and Kulshaw in 2014 and Gades et al. In 2023. And these are coincident with the early stages of the continental collisions. But then in the eastern part, in the central part, we see that we have ages at 1030 and 1020 million years, meaning that they do not belong to the same geodynamic environments, probably, and that they cannot be linked together within the high pressure belt because they're representing very different episodes in the Grenville orogeny building. Finally, if we look at Molson Lake terrain, in here there's only very preliminary ages that were published in a paper from Rivers in 2012, if I remember correctly, that were giving them at something like 1 billion years old, meaning that these are also younging from the western part of the Grenville towards the eastern part of the Grenville. So these three high pressure segments, they show first that there is crystal thickening in the orogenic Grenville, and they're all exposed in here in the frontal part of the orogen, and they do not represent the same moment. At least they're formed diachronously when the orogen is built up. So all of these is published 2 months ago in a journal in Precambrian Research, so you can dig a little deeper in that, and I am available for your questions. Thanks.
Great, thank you so much. Sorry, I was having trouble unmuting myself even now. That was a great talk. Thank you very much. We'll take questions now. I see Carl has his hand up already, and feel free to put your hand up in the using the little buttons, or if you share your screen, I'll know that you're wanting to ask a question as well.
Shall I go?
Yeah, go for it, Carl.
I have a question on your interpretation of lutetium ages. So you have 1030 and 1020.
Yeah.
Do you think that this difference is real?
Yes, I think so. Especially because, in fact, when you look at them, these are errors that are very integrative. They're taking everything into account, and they do not overlap that much. In here, I said 1030, it's 1033, and the other one is 1019, and so on. So they overlap slightly, but differently enough. And also, they don't record the same things, just petrographically speaking. So in that one, we see 2 stages of growth, while the other one doesn't show that. So I think that is quite different. The same for the samarium neodymium, in fact. So for me, there are different stages.
Have you thought of weighing your age towards the areas in your garnet that have the that are the richest in lutetium? Because in your first sample, it's the rim that is the richest in lutetium.
Yeah.
So your age is weighted towards the last increment of garnet growth. You're pretty much dating. It's an order of magnitude difference between your rim and your core. So what you're dating is the last increment of garnet growth. So you're dating your rim. Whereas in the second sample, you're dating your core, which is 10 times more enriched in lutetium than your rim.
Yeah, but when you look at studies that show that when you're dating cores that are even not that much enriched compared to the rims, lutetium hafnium is always skewed towards the core, always, ages. When you look at papers with high precision lutetium hafnium, then you can see that when you do just very specific, the papers I was showing at the very beginning, when you look at them, the rims are always younger than the cores in lutetium hafnium, always, systematically. And,
the rims have to be younger than the core, of course.
Sorry?
The rims have to be younger.
Yes, they have to be younger, but meaning that when you look at them in a bulk situation, your lutetium hafnium age is always going to be skewed towards the core, no matter how much proportion you have in your rims. And in that case, it's something like very, very small, and it's very well averaged, because when we looked at the content, lutetium content in all of them, they're very, very equivalent in there. So we're moving from 0.2 to 0.6 ppm and so on. If I remember correctly, 0.2 to 0.6 or maybe 0.5 ppm in there. And no, I don't think we're dating the rims in that case, in fact.
Okay, so you're interpreting that as propagation of your thrust belt.
Yeah.
Within 10 million years. Okay, thanks.
Yeah. Other questions for Caroline? Jamie? We can't hear you, Jamie.
How about now?
I can hear you now.
All right, cool. Nice to see you. For your SMND results, are you, given the temperatures that these rocks are experiencing, are you interpreting those as mostly cooling ages then? And relatively quick cooling?
So.
Yeah.
Yeah,
okay.
I think so. Yeah.
Yeah.
Yeah, because we're something like 800 to 900 degrees.
Yeah.
And when you look at the grains, they're not that big. So you cannot expect them to be something else than cooling.
Yeah. Are these would that sort of age be equivalent to other constraints on cooling ages in the area?
Yes, in fact, you've got some ages at 980 and so on in the Petrochronological belt. In fact, when you keep going through towards the front and so on, you keep getting younger ages. So it seems to be quite in good agreement, in fact. Check.
And relatively rapid cooling as well, seems.
Yeah. Well, in that setting, yes, I would say yes.
Thanks.
Yeah, Chris.
All right, great talk, Caroline. Well done. The question I have, I'm going to build on Carl's stuff, and I'm going to be mean because that's my kind of personality here. So you have this 10, 20, and other group of ages. Why do you have to group them? Why can't it be a protracted garnet growth over 20 million years, considering that the Grenville is a very long-lived, low, like high temperature, but prolonged? Why can't you just grow garnet over 20 years? Why do we always have to lump things into statistical averages when the actual duration of the process may have been longer than the uncertainties on your individual ages? So that's my rant question.
Yeah. Well, in fact, when you look at it, you preserve all your chemical zoning and your inherited magmatic textures, meaning that you cannot have very, very long stay, in fact, at high temperature in there, else you would have just annihilate everything. So when you look at it, you have in here all your plagioclase that is still, this is your topotactic recrystallization of big plagioclase porphyroblasts into tiny plagioclases, and you don't annihilate those textures. Same in here, when you look at it, here. When you look at it in here, it's a very drastic difference in between your core and your rim, in fact, just in there. It's not completely continuous. So if it was continuous and continuous growth, which is, I think, what happens in very, very common cases, then I would expect to have something that is very continuous in here and not that kind of big jump in between. So I would say that. And that's why I would put them in two different groups. If I put them all together, it gives you 10, 20 plus or minus 10, if I remember correctly, which is what you would expect because it's complete average in between those two.
And just as a quick follow-up, so that's a fair explanation. And just to play the devil's advocate here, why do you have to lump those garnets together to give you 10, 13 plus or minus 5? Is that statistically relevant considering that garnet growth could be more than 5 million years? So that's not the crux I'm getting at. It's more of a question about how we interpret geochronological data in general in prolonged systems. But your answer was totally fine, but I would always want to be the contrarian to it. So thanks for your response, Carolyn.
We have a question in the chat by Richard Everett, who had a question that's something I was thinking about as well. Did the Manicouagan impact have any impact on your study?
I don't think so, because Manicouagan impact is Triassic and we have no Triassic overprint on the stuff. So I would say no, in fact.
Is there much evidence, or do you know of any research that talks about how, like, a shock wave traveling through, you know, a near impact?
I think
like
there must be some papers on that, probably, but I don't know them.
Yeah, okay. Just curious. Thank you. Any other questions for Caroline before we go? Renaud, yeah, go ahead.
Yeah, just one more about those garnet dates. So what happened between 1030 and 1013 to that rock?
I think it's just the ongoing of the propagation of your origin, and it keeps going. Meaning that when you start to propagate, when you start to bury stuff in there, then in here you can just perturbate the equilibrium, you restart your garnet growth at that time. So what's happening in between is not recorded in garnet. It must be happening something, for sure. So it probably starts to be exhumed a bit. But yeah.
Okay, so you don't know if it's garnet that stops growing or garnet that is resorbed, or if the rock is exhumed.
Yeah, if it was garnet resorption, then we will have an increase in lutetium in the garnet rim. So it won't be garnet resorption at that time.
All right, and a totally different question. Those zircons, which you interpret that might be metasedimentary, do they have any tetraedral textures? Like, do you see any rounded cores or anything that would suggest that they could be tetraedral?
No, in fact, and that's why I'm way much more going, because the interpretation of those zircon was quite complex, given how bad they were looking, and but the fact that the whole rock in here are completely fine, whether you have zircon contribution or not, meaning that you're at equilibrium with everything. This gives me a hint that we're not in a sedimentary system, in fact, and we might more be in a very magmatic system, and we have an age, maximum magmatic age at, yes, 1.6, and then lack of successful crystallization. But that's probably because we don't have any partial melting of something. So.
Okay. All right, cool. Thank you. Nice talk.
last call for questions. All right. Well, thank you so much, Caroline, for the great talk.
Thank you.
That was really wonderful. And we'll have our next talk next month by Relly Godard on some paleopiezometry methods. Thanks everybody for joining, and we'll see you next time.